All right, we're going to work on an example of a conventional air-cooled heatsink that you would put on a low-powered CPU. It would work with natural convection heat transfer through air, and of course the heatsink itself, depending on the material, is going to have some conduction. So here I am on the main or the opening window of COMSOL with the new, and I can click on the model wizard to start the simulation. First, I have to define some of the specifications of my model. First is space dimensions. This is going to be a 3D model, so I'm going to click on 3D. Then I'm going to have to pick the physics or the governing equations I'm trying to solve in this problem. Like I said in the earlier, I'm trying to solve a heat transfer problem because it's a thermal management using an air-cooled heatsink. So I'm going to click on heat transfer first, and it tells me on the right panel what this could be used. Used like computer temperature, and that's basically what I'm trying to analyze. So if I click on the arrow next to it, I can see the sub-modules here. And the thing I'm trying to do is a solid heatsink made of either copper or aluminum, some of the two conventional materials used in manufacturing of heatsinks. And if I read on the right panel, it says that it can be used to model heat transfer by conduction, convection, radiation. Conduction and convection are the two methods of heat transfer I'm interested in this problem. So I can double click on this. And then I'll be taken to the next window where I can, well, actually, no, I lied. Here, on the right panel tells me the degrees of freedom that it will solve for, and it still allows me to add more physics to the problem in case I want to do a multi-physics problem, let's say water-cooled heat sinks that we're going to cover later on. But in this example, I'm not doing a multi-physics problem, so heat transfer in solids is enough. So I go to the study part, and now here I have to determine what kind of study I want to do. Stationary is a steady state problem. Let's say you put the heatsink on the CPU and then you wait long enough that the temperatures of the CPU or the heatsink don't change anymore. And that's also written on the right panel that things do not change over time. Time dependent is when you want to see the time dependent or over time results. I'm not interested in that here. I'm interested in the stationary when everything becomes steady state. So once I double click on stationary, I will be taken to the next window, or the main window, where I can determine design and do my analysis. The first thing I want to do is to change the units of length. I don't need to do that, but it's more convenient because COMSOL has it for me anyway. In heat sinks, we're usually talking about microns or millimeters in the dimensions for a base of a heat sink in its height. So I'm going to change the units into millimeters. That's more conventional, but I'm not going to change the units for angles. I'm going to keep it at degrees. So click on the parameters. Again, this is an optional step. You don't need to define parameters. You can just put numbers in the design or geometry part. But if you're doing optimization problems, if you want to change variables that are related to each other in terms of equations or something, defining parameters will make life a lot easier. In this case, I won't be needing to define or relate equations or variables, but I'm going to do parameters anyway for convenience. So I'm going to define a parameter called W of B and give it the length 25. So the base of my heatsink is going to be 25 millimeters by 25 millimeters. In each direction, it's going to be square base. So I'm going to put mm in between brackets. And when I press tab or enter or click somewhere else, COMSOL converts my 25 millimeters into 0.025 meters. That's what convenient for COMSOL, and this is what is convenient for my human brain. Then I can change or give a description in case I want to come back to this problem later on and I want to remember what I did. So this is the base width. Then I want to define another parameter called TB, and this would be used to define the thickness of the base. I'm going to say 5 millimeters for the thickness of the base, and call it base thickness. I need to move some cable here so it doesn't make too much noise. All right, so the next thing I want to define is a parameter for the thickness or the width of the fins that are going to be mounted on the top surface of the base. So let's call this W of F, and it's going to be 1 millimeter in length, and that's going to be fin, let's call it width. The next thing is the height of the fins. So it's going to be, let's call it LF. And let's say this is 15 millimeters. I'm going to have fins which are 15 millimeters high, and I'm going to call this fin height. And then I want to define another parameter, which is the spacing between the fins that are going to be mounted on the top surface of the base. I'm going to call it WC, and that's also the spacing. I'm going to give it 1 millimeter, and that's going to be fin spacing, or we can also call channel width. As you can see, I made an error here, and when you make mistakes like this, COMSOL tries to notify you by changing the color of the text. In this case, it's orange. It's telling me there's a warning here. MMM is not a recognized unit, so I just have to type MM and click, and now all of the parameters are properly defined. So with that, I can come to geometry and design my model. So for the base, I have a block which has a square cross section for the base, and then it's extruded or have a length or width, height of 5 millimeters. So for that, it's easier to just create a block and give the dimensions here. The width and the depth are going to be the dimensions of the base in the X and Y direction. So I'm going to call it the same thing. It's WB and WB. If it was not a square base, then you would change these appropriately. And for the height, which is the length of the base in the Z direction, I'm going to put TB, which I have defined up here. So if I build selected, I see a cube or a block designed by the dimensions that I've given. The one thing that didn't work, or I didn't specify, was the location of the corner. Right now this corner is at 0, 0, 0. But what I want to do, and it's not necessary, but I want to do it because it makes life a lot more easier for me. I want to put this corner, the bottom corner, at minus 12.5, minus 12.5, and 0. So with that, I can say this is minus WB divided by 2, and this is minus WB divided by 2. And I'm not going to change the Z, and I build selected. Now this is moved. Let me also change the view and zoom to all. If I look on in the XY plane, I see that this is minus 12.5, minus 12.5, and the Z part is equal to 0. So that's the base of the CPU, or the heat sink. Now what I want to do is to define or design some channels on this heat sink that would enable, or that would act like fins and enable convection heat transfer. One way to do that is create another block. Another to do that is to design a rectangle and extrude that. I'm going to go with that step so you know how you design a 2D entity and extrude that. So because this is a 2D and I don't see any options of 2D modeling up top, I need to go with a working plane or work plane, where it allows me to design 2D entities, and then I can come back to 3D and extrude that page or that entity. So I'm going to click on work plane, and the first option is a quick, which then enables me to define a plane in each of these regular planes, X, Y, Y, Z, and everything. And I can also give an offset. In this case, it would be TB. So if I do this, it would bring the plane right here. But there is another way, if I don't want to give numbers or anything, is to go into face parallel. And now I have to pick a face on which I want to make a working plane, which is the top surface of the heatsink. So if I click this, and if I give a distance, it could go up or down, offset from this face. I'm not going to give that because I want to actually design my channels or fins on the top surface. So when I'm satisfied with this, I can click on plane geometry. Now this is a 2D design environment, and the options I have up top in this ribbon have changed accordingly. So I'm going to create a rectangle. with the width of the fin, but the fins are going to run along the length of the um, base, and the length of the base was WB, and I want to put the corner right here, which was, if you remember, minus WB divided by 2 and minus WB divided by 2. So if I say build selected now, I have one fin designed right at the edge of the base on the top surface. But I want to have an array of these in the horizontal direction. I want to cover the entire surface of the base. To do that, to make multiple copies of one entity, I can come to transform and then pick array. And now the first thing it's asking me is, what entity or object do you want to copy? So this is the only thing I want to copy, so I click that. And then I have a few more options to respond to. How many copies in the X direction and how many copies in the Y direction? If I keep 1, 1, so there's not going to be any copies in either direction. But I know that I'm going to have 13 fins in the X direction and nothing in the Y direction. So I'm going to change this to 13. And here, the third option is the distance between these two, between each of these copies in the X direction and the Y direction. Since I'm not going to have any copies in the Y direction, so I'm going to keep this as 0. But for the XW, I have to give the distance between the top left corner or bottom left corner of this fin and then the bottom left corner of the adjacent fin, which is going to be equal to the thickness of the fin or the width of the fin and the width of the channel. So I'm going to say WF plus WC. If I say build selected, I have 13 fins, or at the base of the fins, copied in the X direction. So come back to plane geometry so we can extrude that, and I say or work plane, and then I see nothing. Seems like it didn't work. Well, it worked. The only one step I have to do is to say build selected, and I can see that the work plane that I created earlier just showed up in here. Now this is a 2D work plane. I want to extrude that. If I come to the top ribbon, the 3D options are available. One of them is extrude, so I can click on extrude. So COMSOL is smart enough to figure out what I might be meaning to extrude. And this is a simple model, so it's probably a good guess, but sometimes it's not exactly like that. I might actually want to extrude like one of these faces. But in this case, this is correct, so I'm not going to change that. The only thing I have to change is the length I want to, or the distance I want to extrude these. If I come back to my parameters, I call that LF. So let's put that LF over here. And COMSOL is case sensitive, so I want to make sure that this is capital L, lower f. And if I say build selected, if I zoom out, I see that I have a heatsink. Right now, this might not be a good, or might be actually a good heatsink depending on the length of the fins. And if I wanted to change the length of the fins, I can come here and say change it to 10 and then say build selected, and the length of them will change accordingly. Once we're done, I'm going to change the parameter back to, let's keep it at 10, it doesn't matter. Once we're done with creating our geometry, we can click on geometry here, and then we can say build all. And the reason we do that is there's the form union option in here, which is a smart way for COMSOL to determine if there is overlap or common areas between entities. Like if you look at here, the bottom surfaces of the fins are touching the top surface of the base, so COMSOL will take care of that. And when we want to do meshing, COMSOL will recognize this, which is making our life a lot easier, and it's a very time-saving option that not all FEA programs possess. So with this, we're done with the geometry. The bottom surface of the heatsink is where we're going to apply some heat flux, simulating a CPU, and the walls of the heatsink are going to, or the fins are going to be where we have convection heat transfer. But before that, let's define a material. I clicked on this, and you see there is a red cross in here because none of these entities or objects in my model have a material associated with them. So right click on the materials and say add materials from library, And let's go into built-in. And also there are some physics dependent materials like MEMS and piezo. But in this case, I'm happy with the built-in, and I want to pick, let's say, copper as a better heatsink material. And right now, if I look at here, all of the domains have the same material, right? Sometimes, as we will go into more advanced problems when we have water-cooled heat sinks, that would not be the case, so we have to make sure that the right materials apply to the right domains. So here, everything is fine. If I scroll down, I see that 3 of the material properties for copper have check marks. Those are the properties that will be used in the simulation: conductivity, density, and heat capacity. Right? Others are not relevant. For example, Young's modulus is only good for structural analysis, but we're not doing structural analysis in here, so I don't need to worry about that. And if I click in materials, and if I see that red mark goes away, that means that the materials have been properly defined. Now, having done this, the next step is to define the boundary conditions and the loading, right? So if I click on heat transfer, I have to make sure that everything is in blue, and COMSOL by default converts everything to blue. That means all of the selected or objects that are in blue are going to be used in the heat transfer in solids physics. When we have multi-physics problems, we have to make sure that, let's say if you have fluids, the domains which are for the fluids are appropriately selected and not included in the solid. The first thing I want to do is to give the heat flux at the bottom surface of the heat sink, which would be simulating a CPU. So right click on the heat transfer, and this is a boundary force. So I'm going to look at boundaries with these icons, and here's a heat flux. So I click heat flux. The first question is where or which boundary has this heat flux. So I'm going to click here, and then the type, flux type, we have a few options. I'm going to pick heat rate, and I'm going to say, let's say there is like 40 watts of power given into this bottom surface of the heat sink. So that's where the heat sink is, that's where the heat is going to be generated or incoming into the heat sink. Now we have to define the outcome or output. Where is the heat getting removed from? And that is the convection heat transfer from the walls of this of these fins. So again, right click here. This is again a boundary force, and convection is also a heat flux. So if you click heat flux, we have the option of convection heat flux. If I click on that, I have to give the heat transfer coefficient. Let's say for air it's about 24, 23, and I'm going to keep it at 293.15 kelvins, or I can change the unit to Celsius, but 293 is about 20 degrees. So I'm going to keep the temperature at 293.15 kelvins as the room temperature. I'm going to give H at 24, but we have to measure H, or convection coefficient of air. There are equations that we can use to determine what the correct coefficient is. And then I have to pick where this convection is happening. Well, on the walls of these fins, but there is a whole bunch of them. It's not like one area like this that I selected for the previous case, right? And to do that, the easier way is to do select box. So let me change this into the YZ plane that I can see a 2D view, and make sure that I'm selecting boundaries, and it's check mark next to select boundaries. And then if I select box, if I go here, do a box, everything which is inside the box will be selected for the heat transfer, and they're all in blue, right? So if I zoom out a little bit with the middle, the scroll button of the mouse, I see all the selected areas that will be used for convection heat transfer in here. Well, I can remove these surfaces if I wanted to. I want to keep them there, but just showing you, if I didn't want to have convection through these base or top of the base, I could deselect them. Let's look at YZ again, and right next to select, I have a deselect box. So if I click that, if I draw a box, and then using the left key of the mouse, you see that the bases are gone, and they will not be included for heat transfer. But in this case, And for a better representation of what this is, I'm gonna click undo or Control Z and reselect those surfaces. Now, having done this, let me actually save it. I'm gonna call this air-cooled heatsink. And now I want to come to meshing this problem. So I don't need to have a very large panel on the middle. Let's make it zoom all. I can change the element size, make it finer, make it fine, or normal. Let's make it fine and build all. And it will create a heatsink like this. Let's make it a little bit finer to make it look nicer. So again, the finer the mesh is, the more time it will take to complete. So I'm not going to go very fine mesh size, because then it will take a long time and it will be too it will make this video much longer than it should be. So I'm going to stick with this, but for real cases, for real problems, you can make this finer. Also, you don't have to necessarily select this. You can, if you come to user controlled, you can determine the size of the elements, maximum and minimum. We'll cover these later on, but for the sake of this problem, I'm going to get back to physics controlled and make it finer. In the user controlled, you can also make it quadratic instead of triangular geometries like this. But again, for this problem, just to show you the basics, I'm going to stick with this problem, and that's it. All I have to do is to click study, right? So I can do this, and in one of the future problems, I will show you how to do parametric sweep, but in this case, I'm going to stick with this. And one thing I want to do is to scroll this window up so we can see what happens over here in the messages and the progress and the log as we click compute. So if I click compute, COMSOL starts making the matrices, and you can see in the log that it's some stuff going on. It's telling me that it's about 55,000 degrees of freedom to solve for, and in 4 seconds it solved the problem. So I didn't get to see a lot of the progress as it was doing the solution, right? So it seems like the heatsink is not very good because I have 520 Kelvin temperatures, which is a pretty high temperature, or maybe the power that we input to the base was too high. So that means that this heatsink is not great for what we need. And we also gave only 40, if I go back to my heat transfer in solids, 40 watts of power, right? So apparently this heatsink is not a good enough heatsink for this case, and it was 15 millimeter long fins. But again, this is just an example. Let's change it to, let's say, 20 or 25 watts and redo the solution and see what happens. And again, it should take about 4 seconds or so to complete, and the temperature should be lower than that. So it's about 435. It's still too high, but let's stick with this. We're not very worried about that. And now the solution is done. So COMSOL creates some default solutions, and for temperature it uses a heat something, if I can read this, if I heat camera light, but we can change it if you want to. For example, if you pick rainbow, that's the conventional things that have been used by other programs, like red for the maximum and blue for the minimum. So that we can see over here, and that tells me the temperature of the heatsink, right? So I have the temperature at the bottom surface and the temperature at the fins. And if I wanted to change the temperature unit from Kelvin to Celsius, I can just come here in the units, change it to, if I can find degrees Celsius, and replot. Now it makes a little bit more sense. What it is, it's from 161 to 162 Celsius. Is pretty high, so it's not really a good heatsink. We have to reduce the power, or we have to pick a different heatsink for this problem. So I'm not gonna worry about that here. Which is just a simple example of showing you how to design a air-cooled heatsink in this problem. So the other thing I want to do, this was copper, right? And let's say I want to change the material to aluminum just to see the difference in performance. So I can double click or right click here and say add from the materials, the built-in, select aluminum. And now instead of copper, I want to do everything into aluminum. So the first thing I want to do is disable copper, and then in the aluminum, in the domain, say all domains. So now all of the domains are made of aluminum. And remember, the temperatures were about 161 to 162. Now I can rerun this without needing to mesh anything or change anything else. Just recompute and then wait for a few seconds. And I see that the temperatures rise, well, still about the same values, but there's a little bit higher over here, right? Now, higher over here, this is not really professional way of talking about results in FEA. If you want to take this into like a presentation or a conference or a journal paper, you want to be more quantitative than just higher and lower by colors. So let's see what is the maximum temperature at the bottom surface of the heatsink. So for that, I can say come into derived values and then right click in here and say maximum on a volume, on a surface, or in a line. I'm interested in the surface because it's the bottom surface of the heatsink. So I'm going to click surface and I'm going to select this surface. And by default, I have temperature over here. I can decide anything else, but in this problem, I only have the temperature as the degrees of freedom that's solved for. I mean, there are other stuff that I can find. If I go here and heat transfer in solids, I can find other stuff, but really what I'm interested in right now is the temperature. So I click that and I think I close this thing. T in kelvins, maybe I can change it into degree C. It didn't change the, it didn't give me an error. The text is still in black, so it should be fine. Then once you do that, you can right click and say evaluate in a new table. And then it shows me that the maximum temperature is 162.99, about 163 degrees Celsius on the bottom surface. Let's go back to copper. So I'm gonna disable aluminum, redo the copper, and rerun my simulation. And once it's done in a few seconds, I can come back here, and without clearing the table, if I evaluate again in the same table, I see that the temperature difference is about 0.78 degrees Celsius. So aluminum or copper didn't really do much for this kind of heatsink. This is not a very efficient one. It didn't change the temperature as much. Maybe the base is too thick, so we can change that. So let's see. And this is the beauty of parametric designs. So let's make the base half as thick, right? So if I do that, and I kept the LF as 10, let's keep the LFs at 15, and with that I can come here on the geometry. I don't need to do anything else. I just can say build all, and now I have this kind of heatsink, right? So changed according to the parameters I had defined up here. Let's remesh this. Takes a few seconds. Again, I'm not going to worry about the quality of the mesh in this example because I don't want to make the video too long. So I can then say compute. It's going to take a few seconds. And then we have to see that the temperature at the bottom surface, if I reevaluate without clearing the table, goes down to 118.01 degree centigrade or Celsius. Then just out of curiosity, if I disable copper and enable aluminum, change the material, and rerun the simulation, we can see the effect of material. Once it's done, I can come here and evaluate this one, and again, this is about 0.74 degrees Celsius difference. So the material didn't change as much, but changing the design of the heatsink actually did a big difference in the overall temperature of the bottom surface. I did not change the power that I gave to the bottom surface of the heatsink. So we did a little bit simple uh, data processing or post-processing of our simulations. We changed the materials. We saw how we can change the parameters for the heat sink. I did a 3D modeling for the base, and then 2D model and an extrusion for the fins. Also, we talked about arrays in this case, changing the materials, playing with mesh. One more thing let's talk about here before we can close the video is, let's say you want to get information about the quality of the mesh. So if I right click on the mesh and say uh, statistics right here, some information is generated. It tells me that there are 27,393 number of elements, some other information if you are interested in reporting your presentations. And then you can right click on study and get statistics. And then you have to wait a little bit for this one. And then COMSOL will tell you that it solved for 52,134 temperature degrees of freedom and some internal degrees of freedom. And then the total was 52,134 degrees of freedom. There is only 1 degree of freedom that this problem solves for, and that's temperature. That's why this number and this number are the same. But if you have multi-physics problems, or if you have field parameters or field degrees of freedom like velocity or displacement, then these would be a bit different. So with that, I'm gonna finish this video, and later on we're gonna learn heat sinks with hot spots, air-cooled and water-cooled heat sinks.